Good afternoon. Today, we will be presenting our senior design project. Our group is creating an automatic cornhole score tracker. Let's begin by introducing our team. We have Robinson Eselon in electrical engineering, Rochelle Azaula in computer engineering, Ryan Coho in electrical engineering, and Gunnar Schumann in electrical engineering. Cornhole, also known as beanbag toss, is a classic American lawn game that is played with two teams. The objective is simply to get your bag into the hole or to stay on the board for points. Despite its simplicity, it requires a blend of strategy and skill to win. The scoring is also very straightforward. You get 1 point for landing on the board and 3 points for getting the bag into the hole. The game is typically played until one team reaches at least 21 points. First, we wanted to enhance the playability and enjoyment of the game. By automating the scorekeeping process, we aim to help players stay immersed in the game without the distraction of keeping manual track of the scores. We also wanted to develop a system that promotes fair play and allows players to focus more on their strategy and skills. Finally, this project was an excellent opportunity for us to apply our engineering knowledge in a fun and practical way. Our primary goal is to create an accurate score counting system. This system is not just limited to standard gameplay, but can be altered for multiple game modes, giving players the flexibility to customize their experience. Portability and accessibility are also top priorities. Just like a traditional cornhole board, we want to ensure that our enhanced board can be easily transported and set up for a game anywhere. Another major goal is ease of use. We want to make it as simple as possible for players to keep track of their scores. And as for our stretch goal, we plan to enhance the overall presentation and entertainment factor of a cornhole game with additional accessories such as light and sound, making the game more engaging than usual. In order to realize our goals and objectives, we have established the following specifications and requirements that our project must meet. The three that we chose for our deliverables are that our system must account for all three bag states via RFID, being on the board, in the hole, and a complete miss. To keep the game flow smooth, we also want to have a score delay of no more than 5 seconds to ensure a fast-paced game. And finally, the battery should last at least 2 hours on a full charge. We are incorporating 2 game modes into our project. First, we have the normal method, which is the traditional gameplay method that we already went over, and then next we have the cancellation method. In this mode, the points of one team cancel out the points of the other team in each round. Here we have our hardware block diagram. Starting from the left, we can see the RFID tags. These are embedded within the cornhole bags, and when they come within the read range of the RFID reader, their unique ID is picked up. The RFID reader then communicates these IDs to the microcontroller, the microcontroller being the central hub of our system that orchestrates all the other modules. Also, feeding into the microcontroller is our 5-volt power supply being fed through a 3.3-volt regulator. Then, we have several components directly controlled by the microcontroller. We have the hole sensor, which is used to differentiate between the team's different bags, the score display, which is where the current scores are shown, and the LED lights, which are just for added visual feedback. As a team, we have distributed the work based on our areas of expertise and interest. I am handling the RFID technology and its related programming. I'm in charge of ensuring all RFID-related components work correctly and can accurately track the state of the bags on the board. Robinson is working on the lights and Bluetooth speaker integration. This involves programming and implementing the lights for visual feedback and setting up the speaker for audio feedback. Rochelle is responsible for the display and control panel. She will make sure that the scores are displayed in real time and that the control panel is intuitive and easy to use for the player. Ryan is working on the hole detection and microcontroller implementation. This also includes overall PCB design.
For our project, we considered 4 different microcontrollers used on a PCB. We chose between the RP24D, the ATmega32U4, and the ATmega32HP, and the SAM3X8D. The RP24D was the one that we chose because it has 2 controllers for the I2C, the SPI, and the UARTs, meaning we could use 2 different I2C connections at the same time. And the RP24D also had the USB support, so we could power everything through the USB and also upload the code over the USB cable. And also the RP24D is also compatible with the Arduino IDE. This is an overview of the PCB schematic. The RP24D microcontroller is located in the middle of the PCB. On the left, in the red box, is flash memory to store the code and a button to enable the USB upload of the code to the flash memory. At the bottom, in the green box, there is the color sensor that we'll be using for project. On the right, in the blue box, there is the USB micro port that will provide 5 volts to the PCB, and there's also a 5 volt to 3.3 volt DC converter that will provide 3.3 volts to the PCB. The PCB also contains some header pins to connect the other parts of the project to the PCB, as well as some switches. The system will need to identify bags in 2 different scenarios. It will need to identify beanbags that land on the board and also identify beanbags that land in the hole. And depending on which place the beanbag lands will determine the amount of points that will be allocated. For detecting the beanbags that land in the hole, there's a few different options that we could use. The first option was we could have used the camera to detect and identify the color of the beanbags. A camera would be very accurate, but the camera would be more complicated to implement. It would be more costly, and it might require a more powerful microcontroller, as it would need more processing power. The second option was the ultrasonic sensor, which basically it could detect if a beanbag was passing in front of it, but it wouldn't be able to identify the color of the beanbag. And it would require another sensor to identify the color of the beanbag. So we decided not to use this as an option, and we decided to use the color sensor as our option for detecting beanbags in the hole, because even though it's not as accurate, it's accurate enough to distinguish between 2 very different colors. It is very simple to implement and also less costly than other options. This is the illustration of the color sensor in the hole. Basically how this would work is a beanbag would fall through the hole into a cup underneath the boards, and there would be an opening in the cup where the color sensor will be able to look through the hole and identify the color of the beanbag. These were the 2 different color sensors that we compared and decided to choose from. The one that we decided to choose from was similar in pricing and similar in the operating voltage, but it drew less current, and it could also generate interrupts based on the set threshold for the RGB value. This is basically how the software would work for the color sensor. The software would check periodically and would read periodically from the registers on the color sensor, and if the value for the color red was high and the value for the colors green and blue were a low value, then it would know that the color is detecting as red, which would be like a red beanbag, basically.
In our project, the RFID system needs to meet several specific requirements. Our system must have a range that completely covers the cornhole board. This ensures that whether a bag lands near the edges or in the center, it will still be accurately detected as a point. And given the variable ways that a cornhole bag can land, our system must be able to read the tags at any possible orientation. We also need to make sure that our system is precise enough to avoid reading tags that are outside of the game boundaries. This prevents false positives that could inaccurately affect scoring. And finally, we're using compact, lightweight RFID tags in order to keep the size and weights of the beanbags within the ACA standards of 14 to 16 ounces. Here, we have a comparison between low frequency, high frequency, and ultra high frequency RFID systems based on a few key characteristics. As you can see, low frequency has the slowest data transmission, with high frequency being higher and ultra high frequency offering the fastest data transmission. High frequency is high, and ultra high frequency has the highest capacity for multiple reads, which is necessary for our project where there can potentially be up to 10 bags on the board at a time. Low frequency tags are generally the most expensive, followed by high frequency, and with ultra high frequency being the cheapest. We weighed these factors carefully, considering our need for high multiple reads and good coverage. Either high frequency or ultra high frequency presents the most suitable choice for our project. Here, we are comparing different RFID readers that we considered for our project. The MFRC 522 has a range of up to 8 centimeters, operates at high frequency, requires a voltage of 2.5 to 3.3 volts, uses SPI, I2C, and UART communication protocols, and is extremely low cost. The other top contender was the SparkFun M60 Nano, which offers the greatest range of 30 to 60 centimeters, operates at ultra high frequency, requiring 4.6 to 5.1 volts, uses UART communication, and has a significantly higher cost. We initially tried the MFRC 522 reader due to its affordability. However, we encountered significant issues with its read range and compatibility with our requirements. we have selected the SparkFun Simultaneous RFID Reader. Firstly, the M6E Nano offers the most range of the bunch, ensuring reliable detection of RFID tags throughout the entire cornhole board area. Additionally, this RFID reader is designed with user-friendliness in mind, with many online resources. The Nano also supports UART communication, enabling reliable and efficient data transfer between the reader and the microcontroller. There are various types of tags available to us. There are active, passive, and semi-passive tags to consider. Active RFID tags have their own power source, typically a battery, which enables them to actively transmit data to the reader. They have a larger read range compared to passive tags and are typically more expensive and much larger. Passive RFID tags do not have an internal power source and rely on the energy emitted by the RFID reader for operation. They're cost-effective, compact, and widely used in many applications, including inventory management. Semi-passive RFID tags, also known as battery-assisted passive tags, have a battery that powers certain functionalities such as the memory storage and additional sensors. They combine the advantages of both active and passive tags, offering a longer read range than most passive tags while maintaining a longer lifespan. We have opted for passive RFID tags due to their cost-effectiveness, compact size, and suitability for our project needs. With this in mind, we selected the Monza R6 tags, which come highly recommended for their compatibility with our reader by SparkFun. These tags are compact, lightweight, and provide a long-distance read range, making them well-suited for accurate detection and tracking. When it comes to RFID antennas, we consider two main types, linearly and circularly polarized antennas. Linearly polarized antennas emit radio waves in a specific direction, resulting in a focused beam. They're often more cost-effective compared to circularly polarized antennas and can offer a good range for our project. Circularly polarized antennas emit radio waves in a rotating pattern, providing better coverage in different orientations. They're generally more expensive, but offer more consistent read ranges and reduced sensitivity to tag orientation. There may be blind spots in orientations where the tag is not detected. A possible solution we have is putting two RFID tags placed in a cross formation on the bag, facing perpendicular to each other on different planes. This idea aims to ensure that the bag is still detected in a linearly polarized environment. However, this adds unnecessary complexity and potential complication. Overall, we settled between the RP-TNC with linear vertical polarization and the MTI-MT 24-2043 with right-hand circular polarization. Both antennas have the potential to fulfill our needs, but considering the limited time available this semester and the uncertainties surrounding the proposed cross solution, and the setbacks we've considered during the RFID implementation, we have made the decision to prioritize reliability and consistency. Therefore, we have chosen the MTI MT 24-2043 with right-hand circularly polarized antenna. Here, we compare the two methods that we've been considering for scanning bags in our RFID programming, the continuous scan method as shown here, and the vibration delay method. In the continuous scan method, the tags are scanned continuously. We calculate the score after each scan. We wait for 1 second before the next scan, and then we loop through the process. Next, we have the vibration delay method. In this method, we wait for vibration sensor activation, which would be the bag hitting the board in this case. We scan for tags. We introduce an artificial 5-second delay, scan for the tags again, calculate the score based on the scanned tags, and then loop through the process. The continuous scan method provides real-time responsiveness but at the cost of increased power consumption. On the other hand, the vibration delay method offers energy efficiency but introduces complexities and potential scoring delays. Our decision will be based on achieving a balance between responsiveness, power efficiency, and overall system reliability during the testing phase.
Moving on to the score display. The score display's purpose is to output the player's scores after each round. This provides ease of access for the players so they don't have to memorize their scores every round. As you can see, there are 3 types of ways we can install the score display, which is either flush into the back wall, have a foldable arm attached to the side of the cornhole board, or on the front lip of the cornhole board. After careful consideration, our group has decided to install the score display flush into the back wall of the cornhole board. This is due to the fact that the score display may get damaged if beanbags were to accidentally hit the display. Moreover, students have to walk to the cornhole board and collect their beanbags after each round, so there would be no added work for players to see their scores. Moving on to the score display's popular technologies. The most popular ones we have seen are either the LCD 1602 module or the 4-digit 7-segment display. Both have the same advantages, which are they are very inexpensive, low power consumption, low input voltage, requires minimum number of pins. They're compatible with any microcontroller, and the brightness is adjustable. However, the disadvantage of the LCD 1602 module is that the display size is very small, and the 4-digit 7-segment display's disadvantage is that it is more expensive than the LCD 1602 module. When comparing parts, we had initially chosen 3 parts, which is the L1602 module, the 1.2-inch 4-digit 7-segment display, and the P10 red LED panel display. On the far left-hand side of the table are our specifications in which we need for the display to be optimal. We have, as you can see as well highlighted in yellow, we have chosen the 1.2-inch 4-digit 7-segment display because it met most of our requirements except for thermal protection, but we can compensate for that by providing a heat sensor. The P10 red LED panel display is just consumes too much power. It's too large for our cornhole board to be mobile, and it is using too many pins. The L1602 module, it has about the same specifications as the 4-digit 7-segment display. However, the display height is just too small, and we'd rather spend a little bit more to have a good display size. For our control panel, the overview and purpose is to provide a user interface to interact with the automated cornhole board. There will be an on-off toggle switch, a button to calculate and display player scores. There will be a button to reset the player scores, 2 different buttons for each game mode, and 2 buttons for each player to manually override the player's scores, just in case inaccuracy does happen. The design is as follows from left to right and will be installed into the back wall, flushed into the back wall of the cornhole board. To pick and to research our switches, for our push button switches and our toggle switches, there are many types. First, the main type is either maintained or momentary. Next, there is a switch connection type, which is single pole, single throw, single pole, double throw, double pole, single throw, and double poles, double throw. The poles indicate how many circuits the switch is connected to, and the throws indicate how many conductive positions it's connected to. There are also many types of materials. The most popular encasing materials for your switches are either high resistant plastic or rubber, and you can have additives such as provide a waterproof cover over your switch or an embedded LED on top of the switch as well, or both. So for our toggle switch, we want this to control the power supply of the score tracking system, so it's only controlling one circuit. So we need it to maintain, meaning we need to have that switch in one position at all times. It's only controlling one circuit, so it's a single pole, single throw, and we want to have an LED indicator to show that the player that the automated cornhole tracking system is working and is on. The distributors are eBay, Amazon, and AliExpress, and as you can see, they're providing the same specifications. So in this case, we're going with price, which is at $2.99 for Amazon. So for our push button switches, we are going with no LEDs, and with LEDs, they are going to control the reset buttons, override score buttons, and the manual score display buttons. They are maintained, or they are momentary, single pole, single throws, and they contain no LEDs for those type of buttons, due to the fact that it does not need to be in one position the whole time and is controlling one circuit. The distributors have all the same specifications, so in this case we're going with price again, and the cheapest is AliExpress at 46 cents. Now for selecting the game mode button, we want the player to know what game mode they're in at all times, so we want an LED indicator, but same type of switch, momentary, a single pulse, single throw button switch. Again, the distributors have very similar specifications, but AliExpress has a 2 amp rating, which is just what we need, not anything higher, and is priced at 58 cents. And also you can see for both our score display and control panel software design, we're using the Arduino IDE environment, which uses the C and C++ programming language. This works best and is most efficient for system processing and embedded systems. And since these components are heavily embedded systems, Arduino IDE was the best and most efficient system to program our software in. And as well, from left to right, you can see our software flowcharts. On the left-hand side, the players throw their beanbags, press the calculate display scores button. The MCU will then read the calculate scores button as high, and the software calls the pre-program function to make the MCU take no more inputs, and they will calculate the scores and store them in the variables, and the software calls the display scores function and transmits the data onto the display buffer and will display the scores accordingly. And depending on whether the score is shown as correct or not, if it's not, the players can override the scores, and if it is, the MCU will decide if the score has reached 21, and if it has, an LED light pattern will show, and if it's not, the players will collect their respective beanbags. And on the right side, you can see it shows how a player will choose a game mode. Depending on what game mode, the MCU reads that selected button as high, and the software will then call the pre-program function to calculate scores with pre-designed formulas, and then set that selected state button variable to high and the unselected state variable to low. And from then on, the players can begin to throw their beanbags.
Our team was looking for a speaker with stereo quality sound that also came with a 3.5 millimeter audio jack connection. There are 2 speakers in which we were considering. The first was the Manhattan stereo speaker, which has a simple plug-and-play setup where you can connect the speakers to a device and just enjoy them. The outputs of this speakers consist of 2 separate speakers, one for the left channel and one for the right channel. They are small, making them convenient to use in limited spaces. The speaker we compared it to was the Lenru A39 Pro. It also comes with a stereo sound quality and comes with a compact design for easy to use. We decided to go with the Manhattan speakers for its lower cost and its dual speaker setup. For the lights, we went with the Altove LED strip for the flexibility between the sizes and the prices. For our power supply and power system, we decided to go with a power bank. There was consideration of using a battery pack for power, but some of our components are powered through USB, so we decided to use a power bank instead. The selections for them were between a 15K milliampere hour or a 10K. We decided to choose the latter, which is the 10K one. So the Van Yust power bank, both supplied an input of, both came with an input of USB Type-C, but only the Van Yust came with an output of Type-C along with 2 USB 2 ports. We approximated the power usage of the major components of our automated tracker to determine how long the battery would go on a full charge. We came up with around 6.6 hours. This will give enough time for the consumer to play multiple rounds during any type of event. The way our power system will be handled is For the MCU and the color system, they will be using a DC to DC converter to regulate the voltage down to a 3.3 volts, and the rest of the electrical components will be using the 5-volt supply from the power bank. At the end of Senior Design 1, we estimated our budget to be around $700, and our goal was to not exceed $1,000. With the most expensive item being received, we are around that budget, and doesn't seem like we'll be exceeding either. Progress has been made for most areas besides the testing. That is because it's about the testing with the PCB and how all our components will work together, controlled by the MCU. Overall, individual testing with our components are working. Plans for success and for the future. What we would like to do is finish the RFID testing, finish our program processor, test our PCB, complete, and test our final prototype. And if there are any questions, we'd be glad to answer. Thank you.